Assalamu alaikum guys, welcome to Chemistry World and I am Wahaj Khalil. Today's the topic of our lecture is the mechanism of acylation of benzene in aromatic substitution reactions. So watch the video till end and stay tuned to get more video lectures. Thanks. Assalamu alaikum and welcome to Chemistry World and I am Wahaj Khalil. Today's the topic of our lecture is acylation in aromatic substitution reactions. The mechanism of acylation. As we know that for aromatic substitution we have to follow the three main steps. Before these we have to see the general reaction for acylation. We need a benzene ring plus acylating agent. We use commonly RC double bond O Cl. Acyl halide. For acylation we have to know what is acyl group. So this is termed as our acyl group. For further proceeding this reaction we also use a catalyst. Commonly we use AlCl3 and our product is the acyl group on the top of benzene here. Sorry. C double bond O and here we have Cl, sorry no Cl, here we have R. Plus HCl plus AlCl3. The catalyst returned to its original position. The first step for this reaction's mechanism is making of an electrophile. Making of an electrophile. For the making of electrophile, we have to react our reagent with our catalyst RC double bond O. Here we have Cl. We know that Cl have 3 lone pair plus AlCl3, which is our catalyst. This Cl attacks on the Al of our catalyst and it will become R C double bond O. Here the positive sign originate and it is our electrophile. Electrophile means electron loving and electron poor species. Plus AlCl4 minus as a base. The second step in aromatic substitution reactions is making of pi and sigma complex. So the second step is making of pi and sigma complex. For this purpose our aromatic ring, the nucleophile, attacks on R C double bond O and here it is positive. So this attack is on the positive carbon and we will get our first complex, which is transition state, termed as pi complex. This C is positive, double bond O, here R. It is our pi complex, the transition state. Pi complex, the transition state, it is not for a long time and this will immediately convert it into transition state, which is termed as sigma complex intermediate. we will show it as follows because it is conjugated and delocalized. Here we have C double bond O R. Here we have H. It is our sigma complex. Intermediate because it is conjugated and delocalized. The third step is removal of H positive from sigma complex. Removal of H positive from sigma complex. For this purpose, the reaction further proceeds in this way. Here we have C double bond O, or positive, sorry, in this way, H R, and this H, and also we have a base AlCl4 minus, which is made in the first step. It attacks on the H of sigma complex, and we will get our product in the form of ketone. Here we have HCl plus AlCl3. Sometime in this position, another complex may occur, which is also a transition state. Here positive, C double bond O, and here we have R. Here we have H. Sometimes the base react with this O, AlCl4 minus, in this way, and here positive dotted bond. But it is a transition state. The final product we got is, as we discussed above, this Cl minus attacks on H, but sometime it is the reaction will go to this transition state and then forward to get our product. There is no acylation in acylation. So there is no acylation, polyacylation, as the alkylation. There is a polyalkylation in alkylation, but there is one drawback, which is that there is carbonylation. If we use the reagent like or here or here or here, here C O and Cl, this will automatically convert into R, here positive plus CO plus AlCl4. Here we have AlCl3. So it is termed as carbonylation. We can also use other catalyst instead of AlCl3. Formylation can also be proceeds. Formylation can also be proceeds by carbon monoxide HCl instead of AlCl3. We can also use the alkylation, oh sorry, acylation for ring polyers. If we have a ring like that, the upper one has C double bond O, here also C double bond O, this O, so we can react it with AlCl3, AlCl3. Here we have our aromatic ring C6H6. So this O will attack on the Al and the transition state occurs. Here AlCl3, this O will become positive and it is intermediate state, and it is also written as to overcome this positive, this bond will be doubled and this carbon will be positive. Oh. So in this case, this molecule delocalized. Somehow the positive sign occur on this carbon and somehow on this O, and the aromatic ring attacks on this carbon when it becomes positive, and we can get our product. We can go to the next page. Just like that, this carbon will form a bond because it is attacked by the aromatic ring in this way. And here we have carbon, double bond O and OH, because when it attacks, this will become here as an intermediate, as we know that, and this O is attached with AlCl, this O will attached with AlCl3, and still positively charged, still negatively charged, and have lone pair here. So here is our carbon. This bond is with that. This O has now two bonds, with the one with carbon and one with AlCl3, but it attacks on that H and leave AlCl3, and our aromatic ring regain its aromaticity. There is C, OH. This C is with double bond O, and here is also our double bond O. The reaction proceeds and we give H2SO4 to this reaction, H2SO4. This OH, there is a lone pair attacks on the H positive of H2SO4 and become the structure is just like that. Double bond O. Here we have now OH2. So this OH2 release from this side, and we will get our ring closure. Sorry, here we also have a double bond O, and we can get our ring closure and product in this form. One C double bond here and one C double bond here plus H2O. So in this form we can get a ring closure by doing an alkylation of the product, which is shown here in this form. Formation with this product with this reactant. The reactant is just like that. So we can get a ring closure here. This is our product. So acylation can also be shown by kinetic model. So it is very easy to show its kinetics. We can write the equation here. We can write RATE, rate is equals to K ARH, aromatic ring, and our reagent are C double bond O Cl plus our catalyst AlCl3. So it is kinetic and rate of the reaction. We can use other reagents like RC double bond O OH, this carboxylic acid group. We can react it with H2SO4 as a catalyst. If we use RC double bond OOH as a reagent, then we should use acid H2SO4 as a catalyst, and this will become RC double bond O OH2, and this OH2 releases as water, and the positive sign is here. We can get our electrophile in this way. So in today's lecture we had study about acylation. First of all, the general reaction of acylation, what is acyl group, the catalyst and the product, and then the mechanism. The first step of mechanism is making of an electrophile. For that purpose we had react the reagent with catalyst, and we obtain RC double bond OC as our electrophile plus AlCl4 minus as a base. The second step is making of pi and sigma complex. This electrophile is attacked by our aromatic ring, and pi complex is shown as follows. It is immediately converted into sigma complex. Then the third step begins, which is removal of H positive. This reaction will occur between this sigma complex and the base AlCl4. Sometimes the transition state like this can occur, but mostly this Cl minus attacks on H, and we can get our product in this way. Further, we had discussed some only one drawback of acylation, which is carbonylation. In carbonylation, if we take this type of reagent for making our electrophile, then carbonylation occurs and our electrophile is just like that. After that, we discussed that we can also use other catalysts like COHCl instead of AlCl3 for formylation. Furthermore, we had discussed that we can use acylation because there is no polyacylation. We can use acylation as for ring closure. For that purpose, we need this type of compound which react with AlCl3 in this way. It is the mechanism between these. It will unstable this compound, and the positive sign occurs on C. Here the aromatic ring attacks on this carbon, and we can get this structure. This is an intermediate, and this O react on the H of the aromatic ring, which is now in this position act as a sigma complex or intermediate, which is in this position it is in intermediate state, and we can get this one. The O further react on H2SO4 and disbalancing itself and become H2O. Here H2O releases and we can get our product in the form of a ring closure. Further, we had discussed the rate which is rate is equals to KAR C double bond OCl and AlCl3. Then we had discussed that we can also use other reagents like RC double bond OH, but for this type of reagent we can use H2SO4 as a catalyst and we can get our electrophile. So guys, if you liked that lecture, please share, subscribe, and don't forget to press the bell icon.